Okay, now we're going to solve Schrodinger's equation for the atomic potential, which is one of the coolest and most applicable solutions to Schrodinger's equation. And when we do that, we can get all of the allowed states of the electron in the atom. So basically, the atomic orbitals and their corresponding energy levels. So let's start by adding a page here to our tab of potentials that we're accumulating for the atom. We need 3 controls to define our atomic potential here. The first one is the charge of the nucleus in elementary charge units. So a proton in the if we're doing hydrogen here, the single proton in the nucleus has a positive charge of 1. We need the nuclear mass, which the mass of a proton is like 1.007 something. And we need the angular momentum quantum number, L. And actually, the only reason we need the angular momentum quantum number is because we are solving this in 1 dimension. And in real life, an atom, of course, the electron is confined to the nucleus in 3 dimensions. An atom is 3-dimensional. And if you're solving this in 3 dimensions, you don't need to specify the angular momentum quantum number. The p and d orbitals and so forth will all just fall out naturally when you solve the equation. But if we are going to solve this in 1 dimension, we don't have those angular boundary conditions, obviously. So we need to account for the angular momentum indirectly with using something called an effective potential. But we'll get to that. Let's do the simplest stuff first here. So we're going to add another case to our block diagram as well. And just like before, we're going to put a for loop in here so that we can scan over all of our x values and calculate the corresponding potential energy for it. And we can go ahead and wire up our x values because those are going to remain unchanged. And we can wire up our dx because that is going to remain unchanged. And we need to grab all of those controls that we just made. And you might think we can just wire up our mass directly to our mass input on our Hamiltonian, where it is used to construct the kinetic energy operator in the h bar squared over 2m. However, that is not the right mass for that. The nucleus is not the confined particle here. And in fact, and the electron mostly is. If you solve this using the electron's mass, you get very close to the right answer. But what is more correct is, oops, that's not what we want. What is more correct is to use the reduced mass of the system. So a reduced mass is the kind of mass you use when you're talking about the kinetic energy of relative motion. So 2 bodies moving relative to each other. And you use that, for instance, to calculate the kinetic energy of like a vibrating bond and so forth as well. But that's what you want to use here. You want to use the reduced mass of the nucleus and the electron. But I'm going to wire up all of our inputs to this formula node. We're going to use a formula node because it's going to make it a little bit cleaner to see what all of our what our equations look like here. Obviously, you don't have to use a formula node, but oops, that is x here. So there's our x value, we've got our mass, we've got L, angular momentum quantum number, we've got Z, our elementary charge. And I should specify our units. Mass is in AMU, That's an elementary charge. L is unitless quantum number. Okay, so first thing we need to do is actually calculate the reduced mass. And the reduced mass is usually signified by a Greek letter mu. So I'm just going to define a new variable mu here and make it equal to the mass of the nucleus times the mass of an electron. And in atomic units, or atomic mass units, an electron is 0.0005485799909 grams per mole. I had that written down here. It's not something I have memorized. Divided by m plus the mass of the electron, 1005485799909. So it's the product of the masses of the two bodies over the sum of the masses of the two bodies, and that still gives you units of mass at the end of it. And I can go ahead and make an output for that actually, and wire that up to our mass, and make sure we disable the indexing on that loop, so we just have that single number. Now we need to define the potential. And here's the potential. This is just a Coulombic potential. It is the interaction, it defines the energy, the potential energy of the interaction between two charges, little q and big Q1 here. This is how they wrote. I just copy and pasted this from Wikipedia, actually. This is the format they use, but it's the charge of the first object times the charge of the second object divided by the distance between those objects, times this proportionality constant, which is 1 over 4 pi times the electrical permittivity of free space. So let's define a U and make it equal to the charge of the nucleus times the charge of the electron, which is just always -1, so just make that -z, divided by 4 times pi. You can just type pi, and the formula node will know what you're talking about, times electrical permittivity of free space in units with inverse centimeters, grams per mole, angstroms. Those are the unit systems we're using. Work that out beforehand, comes out to this. And then times the distance between the particles, or the distance between the nucleus and the electrons, r, which we've not defined yet. So got to define it up, got to initialize it up here, and we got to calculate it, and it's just going to be equal to the absolute value of x, because we're going to assume that our nucleus is positioned at the position 0 on our x-axis. And it doesn't matter whether the electrons on the right or the left side of the atom, the distance is still the same. So that's why we use this absolute value. It's not going to affect the energy. But we are going to modify this slightly and subtract 1 times 10 to the -25 angstroms from that, which is just a ridiculously small number. And all that's going to do is it's going to keep r from being 0. Because if we calculate a bunch of points and one of them ends up being 0, then we do this divide by 0 here. And whenever you divide by 0, you get an error. You get not a number value in your array, which can cause all sorts of issues. So we're going to just shift everything by this really tiny amount that is not going to change the energies, but will stop us from getting those errors involving dividing by 0. So add an output here. Oops, what's gone wrong? Oh, this is an input, not an output. Add output. There we go. You can tell by the thickness of the border. There's a difference. Okay, so this should be enough to calculate some s orbitals here. There's different ways to calculate the orbitals, actually, but one of the easier conceptual ways is we're going to start at 0. So this way, like when we're looking at it, this is kind of like it's actually not the radial distribution function yet, but we'll talk about exactly what it means. But this is kind of like the radius, so nucleus and getting further away from it. Notice that I had the auto scale on, and so it looks like something has broken here, but it actually hasn't. It's just that this potential approaches infinity, or negative infinity, as you get to go to 0. So you get these really low values. So you just want to make sure your auto scale is off, and you want to type in something sensible here. And I know from experience that something like negative 200,000 inverse centimeters will give me a reasonable range. And here is our first state. We've got pull that up in a second. We've got our s orbital here. There we go. I'm just rerunning it, made the wave function renormalize there. There's our s orbital, and that is the wave function in a certain coordinate system. And here is the energy level. So, okay, so let's check some things here. Is this the right energy, even though we've calculated this in 1 dimension instead of 3? We can check this in the NIST database. We just need to pay attention to where our 0 energy is defined. Our 0 energy is defined here at the asymptote of the potential. So basically the limit of what is holding the electron into the nucleus. So how much, so this is negative of how much energy it would take to pluck an electron off of the atom, which is the ionization energy. So we can compare our number to the ionization energy. And so here's what you get when you go to the NIST database for and look up neutral hydrogen here to get the energy levels. And you can see they have their energy levels in inverse centimeters too, but they define 0 as the ground state energy. We can't really do that in advance because we don't know where the ground state's going to show up. The asymptote is a more practical, place to define the ground state energy there, or to define 0 rather. But we can compare that if we go down to the very bottom. We've got this. It says H limit. The limit is what this is approaching. It's the ionization energy. So 109,678 point something, 109,677 point something. So, that is off by about 1/1000th of a percent error. So that's pretty awesome. All we've done is include this one interaction in the potential. In real life, there are other factors that contribute very minorly to this energy, as you can tell, because we've almost got it right, such as relativistic effects and like hyperfine coupling between the spin of the electron and the nucleus and all that stuff. But almost the entire interaction can be modeled with just this charge-charge interaction. So that's pretty good. Okay, another thing we can check is the wave function itself. Okay, what have we plotted? This doesn't look like the wave function, the radial wave functions that you see in textbooks. And it's not. There are different ways of displaying a radial wave function. Anyway, the most useful representation, if we square this, is called the radial distribution function. And that is the probability of finding the electron at a certain radius from the nucleus. That is what we're currently looking at here by squaring our wave function by selecting this probability. And by the way, I've forgot to mention I made a minor change to the program here. Instead of using a Boolean click on or off for squaring the wave function or not, I made this enumerated control, which you can make by going to right-click, ring and enum, text string. And what you do is you right-click, go to Edit Items, and you can add whatever words you want to appear in this drop-down box, like probability, or, that spelled it wrong, doesn't matter, wave function. And then, you can select whatever, and it assigns each word a numeric value that you can use in your program. So you can wire that into a case structure or something. So I like this better because then it's easier to tell what exactly you're looking at because you can actually write it out. Okay, so we're squaring the wave function, we get this. This is the radial distribution function. As you can see, there's a 0 probability of finding the electron in the nucleus, which is physically accurate. A maximum probability right here, and then it kind of decays off. Looks like the guitar string wave function probability. Only distorted, just like we would expect. Can we use this to... Is this what this is supposed to look like? Does this make sense? Zoom in on that there. Well, yes, we can check this. One sort of well-known value is called the Bohr radius, which is the distance from the nucleus in a hydrogen atom you're most likely to find the electron. And in some computational circles, that is used as a unit of distance. So one Bohr is 0.529, and does this show up at 0.529, this maximum here? We could try to zoom in and so forth, but we might as well have our program calculate it because, why not? Computers are good at that sort of thing. We're going to use the array max and min sub VI here. Now we can't just take the max from this. I'll just label it so you can see what I'm doing. You can't just take this max value because that's the max Y value that's giving you. You need to find what the corresponding position is on the x-axis. So we want to use an index array, and we want to grab our x array, which comes from way over here. And then we want to take the index that the max value of our wave function occurs at, our probability distribution occurs at, and take that index. And actually we want to insert a square here, which will make no difference, but well, I guess it can, because if we have negative values in our wave function, this will won't necessarily find the largest magnitude. So you want to square your wave function because that makes it the probability distribution, then find the max index, and then we can display that. And that should be some angstrom value of where you're most likely to find the electron. 0.529. So that's pretty good. Okay, so this matches everything that one would expect for a hydrogen atom. Okay, but what was I saying before about this doesn't look like the radial wave function you see in textbooks? Here is what we have. You have your radial wave function you see in textbooks. What we are calculating, because we're doing this in one dimension, is equivalent to r times the wave function if this was a three-dimensional case. The radial distribution function is defined as r squared times the, actually 4 pi r squared, but we're normalizing these, so constants don't matter. But r squared times the wave function squared. Why do you do this? Well, basically because you're integrating over spherical coordinates. Whenever you are integrating in spherical coordinates, if you learned in your math class, you do this silly r squared times dr sine theta d theta d phi sort of situation. That's where this r squared comes from. Why do you need that? Well, if you think about every radius that where you could find your electron as a bunch of, surfaces of spheres, there is more area in which your electron is distributed at larger radii than at smaller radii, because you're looking at the surface area of the sphere of that radii, which is 4 pi r squared. So you can't just take a slice through space of probability, which is what your radial wave function is. You have to use this r squared factor, which is called the Jacobian, to adjust for the fact that your space is more spread out at large radius than at small radius. Not something you have to worry about in Cartesian coordinates, but this sort of weirdness shows up in spherical and polar coordinates all the time. So what we're calculating is equivalent to this. If we want the radial wave function, then we're going to have to divide by r. It's not really something we have to do very often. The radial probability distribution is kind of the most useful thing, actually, but let's just take this. We got our wave function being plotted right here on its own. Just to show you, we can do a divide by r, which is x. Plot what that looks like. And now you see this thing that kind of exponentially increases as you get closer to 0. And we have a weird, we have a divide by 0 error, which is what we were avoiding over here before. So if you want to kind of get rid of that early point nonsense, you can just start not quite at 0 here. There you go. So that's what you'll see in textbooks most of the time, is that. However, I think that gives physically kind of the wrong intuitive picture of an atom, because it implies that, you just square that, and it implies that you're going to find the electron in the nucleus most of the time. And in fact, you never find the electron in the nucleus. And that's because you're not treating your spherical coordinates properly when you're looking at a plot like this. Even though this is technically a wave function versus r, it does not tell you the probability distribution with r. So just a little point of clarification there. Not something we really need to look at for our purposes. So, oops. Don't want to open emails there. I wanted to open this. This is what is equivalent. This is what we're calculating. Squaring it gives us this, which is the radial probability distribution. Just this, conveniently the same way it does when we square the wave function normally. And if you want to get the radial wave function, you can divide by r. Okay. Couple more things. This is only calculating s orbitals, and we can look at the other s orbitals by shifting. There's our 2s orbital. The energy might not be quite right because we're cutting it off. Make sure you are plotting over a large enough space that you allow your wave function to decay to 0 naturally. And I'm going to start at 0 again. That should be our energy of our 2s orbital. We could calculate that here by looking at well, basically our ionization energy minus this energy, which is going to be 20,000 something. You'll find it's very close to this if you do that subtraction. And as you can see, the wave function gets, the probability distribution gets further away from the nucleus, just as you expect for the higher n quantum numbers. Okay, p orbitals. We've not finished our potential if we want to calculate p orbitals. Like I said, if you are doing this in 3 dimensions, the p and d orbitals will fall out naturally as you shift, you'll find them. But they arise because of angular boundary conditions, which we don't have in 1 dimension. You can, however, account for them artificially by using what's called an effective potential, which is writing out the centrifugal potential as a potential energy. In fact, centrifugal forces actually arise from, kinetic energy, and you don't need to, they're not a true force in that sense, but you can treat them as a force by taking the angular momentum squared divided by 2 times the reduced mass times the r squared. The angular momentum in the quantum world is the square root of the angular momentum quantum number times angular momentum quantum number plus 1 times h bar. So we can type that in here. We'll add another term to our potential to account for this effective centrifugal potential. L times L plus 1 times h bar squared, which we used previously in our kinetic energy operator, actually, and that was 33.71152583461. That takes care of our top bit, divided by 2 times mu times r squared. And this is making this line really long, so I'm actually just going to put in a line break there. Formula nodes will ignore all white space, so you can put as many enters and spaces as you want to break up your code. Oops, I have my parentheses all wrong here. I don't actually need this outer pair, so L times L plus 1 times h bar squared divided by 2 times mu times r squared. Cool. Plus your Coulombic portion. That should work. Let's run it. And let's go back to our 2s orbital, because if you remember from freshman chemistry, the 2p orbital for hydrogen specifically, or for one electron atom specifically, has the same energy as the 2s orbital, because the energy is only dependent on the n quantum number unless you have electron-electron interactions. So boom, there we go. Number has changed by like 0.03, which we can probably, get more accurate if we used even more points. We could have that change by even less. But you can see the potential has changed because now we have this effective centrifugal potential that kind of pushes the particle further away from the nucleus, which is, what happens in a p orbital there. So cool, and we could do a d orbital as well by doing L equals 2. And of course, when we do that, we want to make sure, again, we're using enough space here. So let's go out to 30 angstroms. So once you put that electron in the 3D orbital, like, look how far away it is from the nucleus. It can get pretty far away. And what we'll find in the next episode is that, all of these energies will correspond almost exactly to the experimentally observed emission spectrum of hydrogen. So there you go.